In the previous class, we started to talk about how you measure the rate of a chemical reaction, which is called kinetics. I showed that the way you do it is to measure how much of a substance you start with at what's called time zero, and then you measure how much is left after different times. You can graph the data by using a time on the X, concentration on the Y graph, and these come out to be a curve, which is called a time course. If you make several time courses, each one of them can give you the slope of the tangent line at time zero, which is called the initial rate, and also the concentration at which the experiment was done. If you make more than one time course, you can make a second kind of graph where you plot the concentration that you started with at each point versus the initial rate that you got from each time course. For the graph of concentration versus rate, you can write the equation for the graph as what's called a rate law or a rate equation. They all start out rate equals K, and you raise the concentration of the substance to a power. The n value, or the power, is what's called the order of the reaction. The rate constant tells you how fast the reaction is compared to other reactions, and the n value tells you how the rate changes with concentration. Both of these are necessary to calculate in order to completely determine the kinetics of a reaction. We showed in the last class that for each order, the rate changes differently when you change the concentration. If the reaction is zero order, the rate doesn't change. If the reaction is first order, the rate goes up by the same factor as the concentrations. And if the reaction is second order, the rate goes up by the square of the ratio of the concentrations. I showed last time that the rate constant K in a rate equation has units, but I also said that you don't have to worry about these units. All you have to do is plug in numbers. But I show the units in each problem to demonstrate that they work. In this class, we're going to deal with data of both types. You're going to get mathematical calculations done on time courses, which is time versus concentration, and also on the other kind of graph, concentration versus rate. The most important thing in doing a kinetic experiment, a kinetic math calculation, is that you determine first what kind of data you're given, because each one of these types of graphs has different math associated with it. You can calculate the K value and the N value, the order, from either kind of graph, but you have to do different math to do it in each case. So if the data column that you're given has time as one of the columns, you know that you're dealing with the kind of graph on the left. If there's no time given and it's rate instead of time that's given, you know that you're dealing with the kind of graph on the right. We're going to deal with concentration versus rate data first because it's the easiest math and it contains the most information, because you can't even make one of these graphs without several time courses being done. So in this example, I'm starting with the simplest. I can either make up reactions or use real ones, and this one is made up. A goes to products, and if you look at the data, the rate does not change. Because we're using concentration versus rate data, this is the second kind of graph, and that's the one we're going to deal with first. I always ask 3 questions about this kind of graph. that are the important ones. First of all, I want you to determine the order, then write the rate equation, and then determine the value of k. This example doesn't really need any calculating because the rate does not change. And even though I showed it varying slightly, as I told you, kinetics is not perfect in the data you get, but the rates basically don't change. That is the definition of zero-order kinetics. You write a zero-order rate equation by starting out rate equals k, and you can either write concentration of A to the 0 or not, because the concentration of A to the 0 is 1. And since the rate equals k, there's no calculating. The k value simply equals any of the rates. That previous one is kind of almost like not even a problem, but that's where we start with zero order. The time when the math is interesting is when the rate actually does change with concentration. This one is a real reaction where hydrogen peroxide decomposes to oxygen, and I gave you data that people have gathered on this reaction. Again, you can see that we're in the type of data that is concentration versus rate, so we're going to do the type of math associated with that kind of graph. In this problem, I'm going to ask the same 3 questions as in the previous one, but you can't determine the order by just looking, so we're going to have to do some math in order to get it. We talked about the fact that just because there's a 2 in front of the hydrogen peroxide to balance, that does not mean that the reaction is second order. In order to know the order of a reaction, we need to know the mechanism of the reaction, and we don't. All we know is the overall reaction, and so we need to do the order calculation from the data. If you could make a connection in your head right now, it would be a big help. And the connection is that whenever you're given concentration versus rate data, the first thing you're going to do to get the order is to use a technique that I'm going to call the ratio technique. I haven't seen this specifically in a book anywhere, but this is just a math technique which is pretty clear from math work, and I'm going to give it a name so that we can refer to it. You can only use the ratio technique with data that's of the type concentration versus rate. You could calculate the order by graphing the data, but I don't want you to have to graph. I don't want to teach graphing calculators, and sometimes graphing calculators don't even give you a graph that looks exactly like what you would get in a paper pencil graph. And so I want to show you how to do all of these techniques mathematically without having to graph. And the ratio technique is mathematical without graphing. We're going to use these little tables that I showed last time as the basis for this. You can tell what the order of a reaction is if you divide 2 of the concentrations and determine how much the concentration goes up. If you're given a second rate, you can divide the 2 rates and determine how much the rate goes up. If the rate goes up by the same factor as the concentration, that means the reaction is first order. If the rate goes up by the square of the concentration ratio, the reaction is second order. So I want to do a problem to show that. For the data I gave in the problem that we're doing, I picked 2 points, and you could pick any 2 points because I always make the data come out on a perfect straight line or parabola. I just pick the first and third point, and I want to get the ratios of the concentrations and the rates. So I took the two concentrations and divided them. I like to put the big number on the top because you end up with a number greater than 1. It works if you put the 0.2 on the top as long as you do the same thing with the rates. But I just like putting the big number on the top. And I also divided the same two rates with the larger one on top. And you can see that the two ratios both equal the same number. They both went up 3.5 times. Whenever the rate goes up by the same factor as the concentration, that is characteristic of first order kinetics. If you had used two different points, you wouldn't get 3.5 as the number, but they would be equal. What you're looking for is that you get equal numbers. That's first order. So in a first order rate law, it's going to start out rate equals K, and you're going to raise the concentration to the first power. Since all of the points are on a perfect straight line, all you have to do to get the value of K is to plug in one of the points from the data and solve for K. I picked the second point, but you can test it yourself that if you plug in any of the 4 points, you're going to get the same answer that we're going to get in the next slide. I plugged in the rate for that point and the concentration for that point, and I included the units. You don't have to. All you have to do is include the numbers. If you divide both sides by 0.3 molar, you see that the K value comes out in seconds to the -1. All you have to worry about is getting that number. If you were a chemist, you would probably get the K value by doing a graph. I want to show you how that would work. If you look at what the K value came out to, it came out to the rate divided by the concentration. If you graph the original data, the line that I'm pointing to has a slope that equals the rate divided by the concentration. And so another way to get this rate is by getting the slope of that line. The advantage of doing that is because the points will show scatter, you can get the best fit line by the least squares method and take the slope of that line, and it corrects for the error in each point. But I don't want you to do that because I make your points come out on a perfect straight line. So all you have to do is plug in any one of the points and it will work. And we said that even though the H2O2 is balanced with a 2 in front, the reaction came out first order. In this next problem, I want to show you what it looks like if a reaction comes out second order. This is a real organic reaction where a compound called acetaldehyde decomposes. That's not as important as looking at the data. The thing is, in a lot of standardized tests, they will put the data horizontally because it saves space. I like to put it in columns, and so I just took that data and put it in columns because that's how I like to look at it. And again, you can see that even though this equation is balanced with a 1 in front of the acetaldehyde, it is not necessarily first order. We have to tell from the data. So since we again have concentration versus rate data, we are going to again use the ratio technique anytime we have that type of data. This time I picked the middle 2 points. It doesn't matter which 2 points. If you divide each concentration by the other, and the same with the 2 rates, you end up with numbers that are not equal. That means the reaction is probably second order, but you can verify that by seeing that the ratio of the concentrations 1.5 squared actually equals the ratio of the rates. This kind of behavior is characteristic of second-order kinetics. So when you write the rate law, you will square the concentration of the original substance. And we said that just because acetaldehyde is balanced with a coefficient of 1, we can't say that the reaction is first order only from that, because we don't know the mechanism. We have to go by the data. In order to solve for K, all you have to do is plug in a point. I chose the second point in the data. So if you plug it in, you want to solve for K. You divide both sides by 0.2 squared this time, and you end up with E.5 as the K value, and the units are correct for second order. The only thing about the ratio technique is that it does not work for zero order, because if you divide two equal rates, you'll always get 1. The thing is, for zero order, you don't need it, because as soon as you look at the rates, you know it's zero order, because the rates don't change. The thing about those problems that we've done is that there's only one reactant, but you know that in chemistry, you usually combine two things to allow them to react by mixing them. And so we need to figure out what happens with reactions where you have two substances, which I call X and Y. So this case is general, and you can use it for any problem. If you look at the data, you have to pick a concentration for both X and Y. And I picked them in a very specific way. But the thing is, when you pick those two concentrations, there'll be an initial rate at each of the points. And I want you to really do the same questions that we did for the single reactant, except that it just looks a little different. I drew in this picture each of the beakers that would correspond to each of the 5 points. And so in the first point, you're mixing 0.5x and 0.05y. And then I showed the mixtures and the rate for each of the points. The note there is that even though you're mixing two substances, each of these reactions only has one rate. You can follow the disappearance of either X or Y, but the truth of it is the reaction goes as fast as the reaction goes. You don't have an individual rate for both X and Y. If the X and Y are balanced differently, you can put coefficients in front of the rates and things to make it come out so that the rate is actually just 1x. But the thing is, I don't really want to do that because it involves some complicated math. And the only thing I want to do is say that even if you're mixing two things, each beaker only has one rate. In the next slide, I want to show that by showing a reaction that's called the iodine clock reaction. When you mix two substances in this, as in the video that's coming up, it's two substances reacting, and there's an indicator that shows when the reaction is over. You can mix all different amounts of the two substances, but the truth is when the color change occurs, the reaction is done, no matter how many substances you mix. When the reaction is over, it's over, and you can measure the amount of time that it took for that to happen. The rate law for a reaction that has two substances reacting looks a lot like the others, except that both substances are involved and are multiplied. And each one of them has its own exponent, which I called m and n. So there's an order in x and an order in y. So we need to find both m and n. The strategy that you use to do this is that you have to keep one of the substances at a constant concentration while you vary the other one. Then the one that's kept constant does not affect the rate, but the one that's varied does. I'm showing that there's actually 3 points in the data where y is constant, and therefore the difference in rate that you see between those 3 beakers cannot be due to y because it didn't change. Here I copied from the data the 3 points where y is constant, and then you can get the order in x. Since the y values are constant, y can't affect the rate, and so we can use the x values to get the order in x. Because the y didn't change, you can kind of cross it out because it's not going to affect the rate. And then you can pick 2 points for x and rate and do the ratio technique. When I divided the 2 concentrations and the 2 rates, they came out equal, which shows that the reaction is first order in x. And so in the rate law, we know that the exponent on the x is going to be a 1, but we don't know y yet. The strategy is to keep x constant and change y. And there's 3 points where x is the same. And so any change you see in the rate at those 3 beakers has to be due to y. I copied from the data the 3 points where x is constant, and so x cannot affect the rate. I crossed out the x column, and now we have to look at the effect of y on the rate. The thing is, even though y is the only one that could have changed the rate, it didn't. Is that possible? Yes. It just means that the reaction does not depend on y, and so it is 0 order in y. If you look at the rate law in part B, there will be a 1 on the x and a 0 on the y. Because y to the 0 is 1, people will usually not even write the y in the rate law. It'll just be rate equals k times x. There's a concept that we have to talk about, which is called the overall order of a reaction, and all that is just the sum of the exponents. Since the concentrations are in molar and you're multiplying them, the exponents, when you multiply 2 things with the same base, you add the exponents, and that's what the overall order is. So the way you would read this equation is that the reaction is first order in x, 0 order in y, and first order overall. If you want to calculate the value of k, all you have to do is plug in a point, and since the reaction does not involve y, all you have to do is plug in an x and a rate. In this case, you have 5 choices of points to plug in, so I just picked one. So I solved for k, and this is what I got for the rate constant. This example is not in your book, but I think it would be good to do another example because I know people can be confused as to exactly how to do this. So I gave you data for a reaction for R plus S reacting, and I gave you several data points with their rates. I have to give you concentrations of each substance that are constant, because otherwise you can't determine the order in each one. And the thing is, I have to do that in the data, so you don't have to worry about it. So first we're going to figure out the order in R. In order to do that, I have to pick the 2 points where S is constant. so that they do not affect the rate. When you do the ratios, it comes out that the ratio of the rates is the square of the ratio of the concentrations, and therefore this reaction is second order in R. So far then, we know that the exponent of R is 2, but we don't know S. In order to get the S, we have to pick the 2 points where the R is constant. If you pick any other 2 points, it won't give you a valid order for S. So if I do the 2 ratios for S, it comes out that they both change by 1.5, and that means that the reaction is first order in S. So the overall rate law is going to have a square on the R and a 1 on the S. So far then, we know that the exponent of R is 2, but we don't know S. In order to get the S, we have to pick the 2 points where the R is constant. If you pick any other 2 points, it won't give you a valid order for S. So if I do the 2 ratios for S, it comes out that they both change by 1.5, and that means that the reaction is first order in S. So the overall rate law is going to have a square on the R and a 1 on the S. So the overall order is 2 plus 1 or 3, the sum of the exponents. So this reaction is third order overall. Here's another example in the book where you have a rate equation that has a square and a cube in it. And so if you add them, that tells you that this is actually a fifth order overall. And the K value would have fifth order rate constants. I don't even know what those are because they're not really of interest, but that's what the overall order is. Now we have to get into the math that you can do with time courses. The time versus concentration graphs, there's a lot that we have to say about, but this is the example of one that I used in the previous class for showing you how you graph a time course. This is going to show the kind of math that you do anytime you have time versus concentration data, which is the first kind of graph shown on this page. And the graph of the time course that we got is a curve. And time courses for first and second order are always going to be a curve because as time goes on, you're using up the substance, which means the less substance you have, the slower the rate is. So this shows that the rate is slowing down. As we showed in the last class, if you do several time courses, each one gives you a concentration and a rate, and that will allow you to make the concentration versus initial rate graphs. The problem comes in is if you only have one time course, you can't even make the other graph because it only represents 1 point. In order to tell the difference between a line and a parabola, you have to have at least 3 points because 2 points give you a line no matter what. So you have to have at least 3. And usually what chemists will do, they'll do several time courses because what it does is it cancels out all of the errors that can happen. For example, let's say you did several time courses and this was the data that you got when you graphed it. More than likely that outlying point is probably an error, and more than likely you can eliminate it. The thing about it is there's a test in statistics called Q subcritical, which allows you to calculate the probability that you can eliminate a data point. And so more than likely, you're just going to ignore the point, and you can get the best fit line by least squares through the other points. The problem is, what if you only did one time course and the one you did was the bad point? That means that your data is useless because it gives you the wrong answer. The question is, why might chemists only do one time course? Well, first of all, it might be too expensive to do more than one. It might be too difficult or take too long to set it up and do more than one. The thing is, if you're going to do just one, you have to make absolutely sure that you do it absolutely correctly. The other thing is that a time course can answer a question that the other type of graph can't. A time course can answer the question, if you start out with a certain concentration, how much will be left after a certain time? Or if you let the reaction go for a certain amount of time, what concentration is left? And you only need one time course in order to do that kind of a problem. So the thing is, there is a mathematical interest in analyzing only one time course, and that's what we're going to do. This is the way a chemist would label a time course. The top point is called the concentration at time 0. And if you let the reaction go for a certain amount of time t, the amount that's left will be the concentration at time t. We want to get an equation that allows you to calculate the concentration at time t after a certain amount of time. In order to do that, mathematicians tell us that we have to, first of all, calculate the area under the curve from 0 to t, then calculate the entire area under the curve and divide them, which gives you the fraction of the area between 0 and t. The mathematical operation that you do to get the area under a curve, which is shown in blue here from 0 to t, is called an integral. So what we need to do is take the integral of this curve from 0 to t. And this is the area under the entire curve, which you can calculate because the x-axis is an asymptote. And if you take the area between 0 and t divided by the total area, this is how you can get an equation. Now, obviously, you don't have to have calculus in order to take this class, but I at least want to show you where the equation comes from that we're going to use. And so we talked about a formula that was for rate last time. You take the change in the concentration divided by the change in time, the negative of it. For first order, that's the kind of equation we're going to do first. So we're assuming that this is a first order time course. If you want to take the area under this curve, you have to write the rate not with deltas, but with little d's, which are differentials in calculus. A differential is an infinitesimally small change. So in calculus, you would write the rate as minus dA dt. And then you want to integrate that function. If you take the integral, you end up taking the integral of a very famous function. You take the integral of 1 over a. You can't really find an integral of 1 over a without defining a function for it. And the function that the integral of 1 over a is called ln, which is the natural logarithms. These are not the base 10 logs that we were using for pH. This is a new kind of logarithm that has a different base. And we're going to talk about that. They work the same way as base 10 log, but the base is different, and so is the value. That's the reason why the first order time equation has ln as part of the formula. This is the equation that you have to know how to solve and plug in things, because this is not calculus. This is just algebra. But I wanted to show you the calculus so you would know where it came from. The variables in this equation are the ones that were on that graph I showed. The concentration at time 0 is the initial. The concentration at time t is the amount left after that much time, and t is the time. The k is the same rate constant as there is in the rate law. The only two kinds of questions you're asked about this formula is because of the fact that the initial concentration is a constant and so is k. The only two variables are time and the concentration left at t. So I can either give you the time and ask you for the concentration, or I can give you the concentration and ask you for the time. And we're going to do examples of each one. The first thing I want to do, though, is show you something about natural logarithms. And if you had college algebra, you've already probably seen this. But the thing is that a logarithm, remember what we said before, a base 10 logarithm is actually the exponent that you have to raise 10 to in order to get a number. And the number itself is called the anti-log, which is usually second log or inverse log on a calculator. The difference between base 10 logs and natural logs is that natural logs have a different base. The ln is the exponent that you have to raise the number e to in order to get the number you're talking about. And e is not a letter, it's a number. You know that the number pi is an irrational number that goes on forever, never repeats, 3.1415, etc. E is just like that. It's a different irrational number that never repeats, and you can consider it to be just like pi. It's kind of a built-in constant of the universe. It has the same status as things like the speed of light and Planck's constant and Rydberg constant and all these other constants that are characteristic of the universe that everything is based on. The mathematical difference for you, when you're doing problems with natural log, the only difference is you are going to have to hit the ln key on your calculator instead of the log key. That is about the only difference for us. But if you take the log of a number and the ln of a number, they differ by this very famous factor 2.3025 something. So for calculational purposes, that's how the log and the ln differ. And the ln always comes out larger. You already know from pH that if you hit inverse log on your calculator, you get 10 raised to the power. But if you hit now the inverse ln, what you get is e raised to the power, because your calculator is pretty smart and it knows that that's what the inverse ln is. So if you want to see the number e on your calculator, if you hit second ln of 1, that will show you what e to the first power is, and that will give you the number. It's 2.71, and it continues forever. So this is what e, or the base of the natural logs, is. You just have to hit the right key for the formula you're using on your calculator. Now for this one, you're going to hang in there with me because you're maybe not going to see immediately what I'm doing initially. But I want to show you the method that chemists use to calculate K from a time course. And in order to do that, I have to show you that the first order time equation is actually in the form of a line. You wouldn't know that by just looking at it, but if you use the property of logs, that the log of a over b equals the log of a minus the log of b, you can you can show it as I did below. You can take the ln of the top minus the ln of the bottom. Then if you subtract the ln of times 0 from both sides and multiply both sides by -1, you get the equation for a line, y equals mx plus b. So if you plot the time on the x-axis and the ln on the y-axis, you will get a line with a slope of -k and a y-intercept of the ln of times 0. And the thing is, if you can calculate that slope, you can get the value of k. If not all that was so clear, this slide shows the real take-home message of what I'm trying to show. The point of what this is that if you plot the time versus the concentration, you'll always get a curve. But if instead you plot time versus the ln of the concentration, you get a straight line. This is what's called linear regression in algebra, turning a curve into a line, because computers can analyze lines much better than they can curves. And so if you can turn a curve into a line, it's advantageous to do it. If you look at the line we get, the slope is -k. And so if you know the slope of that line, you just take off the negative, and that gives you the value of k. Now if you look below, when you're given time and concentrations, the way you're going to calculate the value of k is to do something that sounds weird initially. It says make a third column. What in the world is, you're going to make a third column of what? You make a third column of ln's. So you go on your calculator, take the ln of the first concentration, write it down. The ln of the second one, write it down. And you'll get a list of ln's. Now you can ignore the concentration column, because what you really want to do is use the second graph and get the slope of that line. And everybody knows what slope is. It's the difference in the y's divided by the difference in the x's. So you're going to subtract 2 of the ln's. That's the difference in the y's. You subtract 2 of the x's. That's the difference in the x's, the same 2 x's, and divide them, and that will give you the slope. Now I know that that is not going to be clear immediately till we do an example. So what I want to do is use the same data that we used on page 298 to show time courses last class. And I'm going to ask you 3 questions because I have the data written down below. I want to determine the value of k. And then I want to do 2 other kinds of problems that I'm going to show you that you can do with time courses. I told you that the math for the first kind of graph here, time versus concentration, was going to be different. So I'm showing you now what that math is like, and that's why we're doing this problem. What you want to do to get the value of k is to make a third column of ln's. Whenever you're given time versus concentration data, again, I want you to make a connection in your head. It's not going to be the ratio technique this time. It's going to be make a third column. And I did that. All I did was take the ln of each of the concentration points and write it down. Now you can forget about the concentration column and use the times as x and the ln's as y. In order to get the slope, we only need 2 points. So I'm going to choose the ones shown here. You don't have to graph that ln data, but I graphed it here in order to show you that it actually is a straight line with a negative slope. And we want to calculate the slope. So I chose 2 points that we're going to calculate the slope from. And you know that to calculate the slope of a line, it does not matter which 2 points you pick on the line. No matter which 2 points you pick, you're going to get the same slope. But the 2 points that I picked in the diagram are the ones that I subtracted. And when you do y2 minus y1 over x2 minus x1, you get a slope that's negative. All you have to do to get k is just take off the negative, and that's the value of the rate constant. So here's a summary of how you do this. If you're given time data and you're asked to calculate k, you first make a third column of ln's. This is for first order. We're going to show what you do for second order later. You choose any 2 points and calculate the slope and take off the negative. That's all you have to do to get the k value. But now that you know the k, you can do a couple of other kinds of problems. Part B here says, what is the concentration of N2O5 at 2.75 minutes? I graphed this because I wanted to show it first. If you start at 2.75 on the x-axis, go up to the curve and read across to the y shows that the concentration of N2O5 should come out approximately 0.06 as an estimate. We don't want to have to do it with a curve. We want to have to do it with the actual formula so we get the exact number. Now we want to get it exactly with the equation. So we're going to try to find this out, but using the first order time equation. This is the first order equation that we're going to use, and we're going to have to plug in numbers for everything but the bottom concentration at time t. The time, of course, is 2.75 minutes because it says it in the problem. The number that people have very hard time remembering what it is the concentration at time 0. I have to give you that number in the data. Anytime it says concentration at time 0, you look at the 0 time point, and the number you use is whatever concentration is listed in the data at that point. When we did the slope of the line, we found out that the k value is 0.35 minutes to the minus 1, and so that's going to stay constant for any of the problems we do with this equation. So I plugged in 0.16 for the concentration at 0, I plugged in the k value and the time, and the minutes cancel. The variable on the bottom looks confusing the way it's written, but remember that you read that the concentration of N2O5 at 2.75 minutes, that's what we're trying to solve for. We can't solve for it, though, as long as the ln is in front, and so we have to get rid of the log. We've already solved this equation with log in pH problems, and so we're going to do the same thing, except that this time we're going to take the second ln. So if you take the inverse ln of both sides, it gets rid of the ln on the left, and you get the second ln of the number on the right. And this is that equation that everybody can easily get upside down. So when you solve it, I'm going to do it by the method I showed you. To be on the safe side, you can multiply both sides by the concentration and cancel them on the left. I showed it canceled out here. Then you divide both sides by what's next to the variable, 2.62. I don't care how you do this mathematically, but you have to come out with 0.16 divided by 2.62. Otherwise, it's just not the right answer. So we found out that the concentration is 0.061. And what did we estimate? We estimated from the graph 0.06. So we did pretty good. I'd say we were 1 for 1. The next question that I want to ask is part C. That is kind of the opposite. I want to ask you how long it takes to reach a certain concentration. So I did it on the graph again. If you look at 0.1 concentration and you read across and you go down to the time, it looks like it's somewhere around 1.3, let's estimate. We have to find numbers then to plug in the time equation again. The concentration at time t in the problem is 0.1, and the original concentration is still 0.16, and the K value is, of course, 0.35. So when you plug in those numbers, the only variable that's left this time is t. But this brings up a problem because people want to take the second ln in this kind of a problem, but you don't. The only time you have to get rid of the log by taking the second ln is if the variable is in the log term. The truth is that you can take directly the ln of 0.16 over 0.1 on your calculator, and that comes out to an actual number. The variable is on the other side. So that ln comes out to be 0.47, and now you have to solve for t. If you divide both sides by what's next to the variable, 0.35, you'll get the time. It comes out to 1.34, and our estimate, remember, was about 1.3 from the graph. So I would say we're 2 for 2. The next concept that we have to talk about is what's called the half-life of a reaction. And the abbreviation for this that they use is T sub 1/2. What this is it is the amount of time that's required for the original substance to go down to half the concentration that it was. So the half-life is a time, and you have to have a graph or data in order to calculate it. What I did was show you the time versus concentration data for the same problem we've been doing, the first order reaction, except that I also added time 6 and 8 points. One of the major reasons why people want to calculate the half-life of a reaction is because of pharmacy. The half-life of a drug tells you how long it takes for half of the drug to get out of your system. Let's say you take a drug that has a half-life of 2 hours. Well, in 2 hours, it's half gone. In 4 hours, it's way more. So you're going to have to take another dose very fast. I take thyroid hormone, which is T4 because I'm hypothyroid. The half-life of thyroid hormone is 7 days. So the dose that I took this morning will not be half gone from my body until 7 days from now. Obviously, you either don't have to take it as often, or if you do take it every day, you take a much smaller dose than you would of a drug that has a shorter half-life. When they do it in pharmacy, they oftentimes give rats a radioactively labeled drug at time 0 and measure the blood level at, at each time point as the drug is excreted. If you look at the graph that I have at the bottom of the page, it takes for the substance to go from 0.16 to half, 0.08, it takes about 2 hours. If you start at 0.08, it takes another 2 hours to go to half again. And if you go from 0.04 to 0.02, it takes another 2 hours again. This is characteristic of a first order time equation. The half-life is the same across the whole graph, no matter what concentration you start with. That is not going to be true for second order when we look at that. But for first order, it is. Again, though, we don't want to get the half-life from a graph. We want to do it from an equation. So the way we're going to do this is to start with the first order time equation. And if you are talking about the half-life, how much is left at the half-life? The amount that's left is exactly 1/2 of what you started with. So I plugged in 1/2 A0 on the bottom, and that will give you T1/2. You can cancel the original concentration, and 1 divided by 1/2, of course, is 2. So the half-life equation for first order, we need to solve the T1/2 by dividing both sides by K. So the half-life for a first order reaction is actually the ln of 2 over K, but you know that the ln of 2 is a constant which you can get on your calculator. So if you take the ln of 2, it comes out 0.693. So the half-life equals 0.693 over K, and you can also switch the T1/2 and the K so that if you know one, you can also calculate the other. So for the reaction we've been talking about, where we know the K value, for the reaction we're doing, the K value is still 0.35. So if we plug that in for K, we get a half-life of 2 minutes, and that's exactly what we found from the graph. So I would say we're 3 for 3. Now it sounds like we've done an awful lot, but the truth of it is we haven't really done that many problems. There's a lot of homework problems this time for a very simple reason. It looks like a lot because there's 2 reasons. First of all, I have to give the data in those columns, and each one of those columns takes up a lot of space. Secondly, I have to give you 2 or 3 of each kind to practice, because this is the only homework you're doing. And so there's only about 8 kinds of problems, but it just looks like a lot. If I give you the concentration versus rate, you're going to make the connection that you use the ratio technique. You do the ratios to get the order, and then you can plug in a point to get the value of K. We also did this problem with 2 reactants, and so you use the same process, except you keep one constant. That's the process for the second kind of graph here. If I give you time versus concentration data, you make the connection that you're going to make a third column. You then get the slope, and that gives you the value of K, and then you use the time equation to plug in to get the amount left or the amount of time it takes. That's the math you do for this first kind of reaction where you have time in the data. Now, this is a complete example problem that shows you just about everything we did from the first part of class. I wanted to use this problem so that you could use it as a template to do the calculations on the homework and to learn how to do each of these problems. So it's just a different problem that has everything. So I gave you concentration versus rate data, and we're going to ask the same three questions first that we asked earlier in the class. First of all, determine the order. We're going to use the ratio technique to do that. So I picked 2 points. We're going to get the ratios, and it comes out that the reaction is first order. So I wrote the rate equation. I'm going to substitute the 4th point from the table. So here's the 4th point. When I plug it in and solve, I get the value of K. Now each of the points on the graph, concentration versus rate, comes from a time course. So I next give you the time course that gave rise to the 4th point. The person started with 1.72 and followed the concentrations with time. And from that, we want to determine K. So for time data, you're going to make a 3rd column. Here's the LNs. You're then going to find the slope by using 2 of the points, X and Y. I graphed it to show you that it's a straight line with a negative slope, and we're going to use the 2 points I showed. So I plugged in the Y's and the X's, and we came out with a K value. And it's basically the same as the K value that we got from the concentration versus rate graph. Now you're going to do part B, which says how much is left at 65 minutes. You have to plug in the first order time equation. Here's the concentration of A0 and the time. Here was our calculation of the value of K. So I plug them all in, and I have to solve for concentration at 65 minutes. When you solve, according to the way we've done in the earlier part of the lecture, you get the molarity that's left after 65 minutes. Now, you want to ask how long will it take to get to a very small amount of A, which is way below the concentrations that are in the table. But since you have a graph, you can still do it. A0 is the same. AT this time is that concentration in the problem. And the K value is the same. So I plug in, and I have to solve for T. So when you solve, you find out it takes 209 minutes. The last question is, what is the half-life? Here's the formula for half-life. So if we plug in the K we've been using, the half-life is about 10 minutes. So that means no matter where you start on the graph, you will go to half in approximately 10 minutes. I wanted to show you an example of a real first-order time course that was provided by the Tylenol product literature. This is a time graph where adult volunteers, human beings, were given 500 milligrams 2 tablets or liquid of Tylenol, and the blood levels were measured at various times. So you can see initially there's a peak, and then it starts to decrease. If you say that it started at approximately whatever the units are, 16, it takes about 2 hours to get down to 8, and in order to go from 8 to 4, it takes another 2 hours. 4 to 2 is another 2 hours. So they say that the half-life of Tylenol is about 2 hours. And when the dosage falls too low, which is considered to be between 4 and 6 hours, you have to take another dose in order to keep the pain relief going. That's why you take it every 4 to 6 hours. This is a first order time course, and this is the kind of thing they use in pharmacy all the time. And again, because pharmacy is so dependent on kinetics, we want to do second order equations as well. The thing is, I don't think there's very many second order excreting drugs, but this is always the next thing you learn, because when you get to pharmacy, there are so many different kinetic schemes for how drugs can be excreted. And also, if you're taking a drug over the long term, so you take a new dose every day, what happens is that you don't get these kind of curves. You eventually reach what's called a steady state, so that the amount of drug stays pretty constant in the blood. That's a whole nother kind of kinetics that you study. So if you're in pharmacy, you're going to do a lot of kinetics, and I want to do second order just as an example of the next one that you would do after first. Now, if you look at this curve, I gave you some data for a reaction that's known to be second order. And if you look at the curve, you really can't tell the difference between this and a first order curve. Human beings cannot tell the difference between curves by just looking. First and second order look alike. You have to do it mathematically. Again, we're in the same kind of data, time versus concentration, the first kind, but this time it's a second order reaction, not a first order one. So when you do the same kind of calculus that you did on a first order reaction, it comes out different because the rate law has a squared in it. What you end up with as the integral is the integral of the concentration to the minus 2 power. And this is not a new function. If you're in Calc 2, you would have learned this formula, maybe Calc 1, that the integral comes out to be a to the minus 2 plus 1 over minus 2 plus 1. And if you simplify that, it comes out that the integral equals the reciprocal of a, not the natural log. And that's the reason why the second order time equation has reciprocal, or 1 over a, in it. The thing is that when you could get it from simplifying the calculus, it's already in the form of a line. You don't have to do anything with it. If you plot time on the x-axis and 1 over the concentration on the y, you will get a straight line with a slope of k. So if you get the slope, you don't even have to take off the negative this time. And if you're going to solve problems using this equation, the variables are exactly the same as they were in first order. The initial concentration, concentration at t, the rate constant, and the time. It's just that solving it is going to be different math. So here's the way it looks for second order. Again, just like first order, if you plot time versus concentration, it's a curve. If you want to turn it into a line, though, for a second order graph, you don't take the ln, you take the time versus the reciprocal graph. And that will give you a straight line with a slope of k. So you're still going to make a third column for second order. The difference is that the third column is not going to be ln this time. It's going to be reciprocal. And you're going to take the difference between 2 of the y's and 2 of the x's again in order to get the slope. So it's the same process as for first order. It's just that the third column is different. And I just wanted to show you the second order half-life also. So what I did was take the time equation, put in the t1/2, and also that the concentration is 1/2 of the original at the half-life. And if you take that equation and go through the algebra, which is pretty straightforward, you just look at the algebra, what you come out with is a half-life formula, but the half-life formula for second order has one huge major difference from the half-life for first order. If you compare them side by side, the first order equation does not contain concentration, but the second order one does. That means that for a first order graph, the half-life is constant, so no matter what you start with, you go to half in the same amount of time all across the graph. For second order, though, it does depend on the concentration you start with because the half-life keeps changing. The concentration is involved in the half-life formula. This has implications for the dosing of drugs, and it also has implications to show that the math of first and second order come out different. I wanted to do a complete second order problem here to show you how it's different from first order. It looks a lot the same, except that the math is slightly different. So I'm going to use the data on page 292 that we were showing second order curves with. And first of all, in part A, I want to determine the value of K. This is the curve with the time data. And so whenever you have time data, you have to make a third column. But in this case, the third column you make is not going to be ln, it's the reciprocal. So in order to get the first point, you would take 1 divided by 1.5 and write it down. 1 divided by 1.008 and write it down. And you'll get x for time, and 1 over is y. So I'm going to take the 2 points shown and use them to calculate the slope. I graphed the data, which you don't have to do, but I wanted to show that it is an upward sloping line, and the 2 points we're going to get the slope from are shown on the graph. When you plug in those y's and x's, you get 0.5 as the slope or the k value. You don't even have to take off a negative this time for second order. Part B says what concentration is left at 4.71 hours. You're going to use, in this case, the second order time equation. That's the one I showed you that has reciprocals in it. The time is given in the problem. The time 0, or concentration at time 0, is in the data, 1.5. And we calculated the value of K, 0.5. If you plug those numbers in, the math comes out different. So you first of all take 0.5 times 4.71, and then you take 1 divided by 1.5, and you add them. When you do that, the answer you get is not A. What we want to solve for is A. What you get is 1 over A. And so you still have to solve for A. A lot of people will write 3.022 down as the answer, but it's not the answer. You have to take a solve for A to get the correct answer. So I multiplied both sides by concentration, canceled, divided by what's next to the variable, and that's the answer. So in the amount of time given, it goes down to 0.331. Now, part C says, how long does it take to get to 0.7? You're going to use the second order time equation again. I plugged in the initial 1.5, the amount in the problem 0.7, and the K value is still 0.5. This time I want to solve for T. You first take the reciprocals, and then a lot of people get stuck at this point, but if you want to solve for T, what you have to do is get rid of the 0.667 on the right, and you do that by subtracting from both sides. After you subtract, you then have to divide by what's next to the T, and that gives you 1.52 hours. So that's how long it takes to get to that concentration. Part D of the problem says determine the half-life when the concentration is 0.8. I had to give you the concentration this time because the concentration is in the half-life formula. The half-life formula is 1 over K times the concentration. And so if I plug in the K value and the concentration 0.8, it takes 2.5 hours to go down to 0.4. It would, if you start at 0.8, you go down to 0.4 in 2.5 hours. But if you started with 0.4, it would not take 2.5 hours to go to 0.2, which is half, because the half-life keeps changing. I made this page for myself. I've never seen a page like this in any book I've ever seen. I have to see it all in one place. And so I did it for each of the orders. I wanted to show you the graphs and the equations. You see that there's one little error in the one equation there, but it doesn't really matter because we don't even use that one. So what I did was I showed you in the top row the time courses for each of the orders. You don't have to do very much with zero order, but I did it myself because I wanted to see it compared to the other two. The time course for zero order is already a line, but first and second order are curves, and you can't tell the difference by looking. One way to do it is to do more than one time course, and then you can get the second row of graphs, concentration versus rate. If it comes out to a line, it's first. If it comes out to a parabola, it's second. The third row of graphs is what you can do if you only have one time course. If you take a first order curve and plot time versus ln, you'll get a straight line. If you take a second order one, you get a straight line if you plot time versus reciprocal. The equations for each of these cases then are in the fourth row. The ones that are in boxes are the ones that you need. Normally I put these on the exam, but you're going to be having your book with you when you take the exam. So if you're aware that this is the page where all the equations are, you just have to be able to plug them in. So I showed both the time equations and the half-life. The thing that's interesting, I thought, about zero order is the concentration versus rate graph is horizontal. We talked about that because the rate doesn't change. I did the calculus myself and came out with the time equation and then calculated the half-life. If you look at the half-lives, I think they're interesting. For zero order, the concentration is on the top. For first order, it disappears. And for second order, it's on the bottom. So these three orders are very consistent. Now what I want to use this for next is if you only have one time course and it's a curve, how can you determine from that whether the reaction is first or second order? Because the curves look alike, and you can't make the concentration versus rate graph if you only have one time course. So I want to show you how that can be done. Here's the time course and the data. You can't tell whether it's first or second order because they're both curves. But what you can do is you can actually make both of the third columns, because all this is math. You can take the ln of each concentration and you can take 1 over each concentration, which I did. I don't know if you want to call this 2 third columns or a third and a fourth column. I could see saying either one, but the point is you now have data that you can use to make both of the graphs, time versus ln and time versus reciprocal. This is what they look like. And you can use these pictures to determine which order is which. If you look at the two time courses for both orders, they're curves, so you can't tell the difference. But if you take the third columns and make the other plots, for first order, when you plot time versus ln, it comes out to a line. We know that. But what happens if you take time versus the reciprocal? It actually comes out to be a curve, because that's the graph that's appropriate for second order. So if you take a curve and make those two plots, and it turns out that the ln graph is the one that's linear, that means the curve is first order. For second order, it's the opposite. If you do the ln graph, that's the one that comes out to a curve, but the reciprocal graph is a straight line, because that's the one that's appropriate for second order. I know I have a question on the test, which is just, I give you the three graphs, either the top three or the bottom three, and ask you what's the order. The way you do that is you look at which one is linear. If the linear graph is the ln one, it's first order. If the linear graph is the reciprocal one, it's second order. And this is how you can actually do this if all you have is the data for one time course. You can do this with a pencil and paper graph or on a computer, and you can determine from that what the order is. Now, the next topic that we're going to cover is called thermodynamics. And I want to show you how you can use kinetics to get to the topic of thermodynamics mathematically. So I'm showing you a reaction with two products and two reactants. There is a forward and a reverse reaction because these are equilibrium. The forward reaction has a rate constant Kf, and the reverse reaction has a rate constant Kr. The way you can do this, you can derive mathematically a bunch of stuff, but you have to make too many assumptions. So I just want to give you the idea. The idea is not very complicated. Let's suppose that the forward reaction is the one that's faster. So Kf is larger than Kr. Since the forward one is faster, what's going to happen is at equilibrium, you're going to build up more of the products, C and D. If at equilibrium, then, you plug in the concentrations to the equilibrium constant expression, products are on the top, reactants are on the bottom, so C and D are the most, the KEQ is going to be big. A large KEQ indicates that you're going to get a lot of product, and that's what's called favorable in thermodynamics, because you want to make products. If the reverse reaction is faster, you're going to end up with more A and B at equilibrium. That means that the reaction doesn't occur very well. It stays mostly as reactants. So when you plug in, A and B are going to be larger, and you're going to get a small k. So that is an unfavorable reaction thermodynamics-wise, because you're trying to make products, but you're going in reverse. The thing is, by the time you get to the equilibrium constant, then, you've kind of eliminated the Kf and the Kr. So what the kinetics does is it gives you the ratio of the products to reactants. And after that, the KEQ doesn't really tell you that much about the rate. What the KEQ tells you is what's called the position of equilibrium. That means, do you have more products or more reactants at equilibrium? And that is called thermodynamics. The reason why is that there's a major function in thermodynamics that's called delta G, Gibbs free energy. And we're going to show that that function has a mathematical relationship to the equilibrium constant. So you can calculate the same thing from thermodynamics as you can from chemistry because it gives you the KEQ. Chemists are interested in both of these, and we're going to explain why chemists are interested in delta G, which is something usually that engineers are most interested in. This is the connection between kinetics and thermodynamics, and that's why we're going to study KEQ and delta G in the next class. Before we do that, though, I want to show you that, remember I said that physical chemists want to be able to make predictions from the math of the molecules. So physical chemists want to take a reaction with two reactants and two products, as I showed there. They want to calculate all the math that they can from A and all the math that they can from B, and then determine mathematically what will happen if you mix A and B without ever going in the lab and doing it, to see if you can come out with the correct answers that you can then test against lab work. The thing is, in order to do that for kinetics, you have to have a theory that allows you to calculate the math. The theory is called the collision theory. And the basic principle of this theory is that it's called the collision theory because molecules of A and B cannot react unless they collide. Obviously, A and B don't have a brain. In order to exchange atoms or electrons, or both, they have to run into each other. So theoretically, you should be able to have a reaction that's the fastest possible. And that is called a diffusion-controlled reaction because every collision between A and B gives you the products. There's no way for A and B to bounce apart without giving you the products you want. So the rate is only controlled by how fast A and B can diffuse together or get to each other. And the rate constants for these reactions are very high. You can tell that you have one of these reactions if the K value is around 10 to the 10th. There's very few of these reactions in practice, but people believe that neutralization is one of them. There's no way for H plus to run into OH without making the product water. So the next question comes in, why are not all reactions that fast? The truth is that molecule A and B can bounce off of each other without reacting. There's two requirements that they have to fulfill in order to react. First of all, the molecules have to have enough energy. They have to hit each other hard enough. The second requirement is that they have to have what they call in chemistry the correct orientation. They must be facing in the right direction. If either of these two is not fulfilled, the molecules bounce apart and the reaction is slower than what you would get from diffusion controlled. I want to show an example where we use 4 molecules that demonstrate this. And NO2 is, you can see, is bent, 120-degree bond angle. CO and NO are just 2 atoms, and CO2 is linear. And the thing you have to know about it is that the oxygens are on opposite sides of the carbon, not the same side. The reaction that we're going to study is that NO2 and CO just trade an oxygen. So an oxygen goes from NO2 over to CO to form CO2. The theory is that the only way this can work is if the CO carbon runs into an oxygen from NO2 directly and pulls it off. If you look below, if the two oxygens run into each other, the atoms will bounce apart because the oxygens are not on the same side of the carbon. The nitrogen and oxygen, if they hit each other, will bounce apart because they don't react that way. And the carbon and the nitrogen, if they hit each other, they'll bounce apart. So the fact that there's incorrect orientations makes the reaction slower. But let's suppose that you are going to get a reaction, that the NO2 and the CO are facing the right direction, and that they are about to react. Now we got to talk about what happens during the collision. The theory is that as the CO collides with the NO, the oxygen has to start to move towards the carbon. So the bond between the N and O breaks, and the bond between the C and the O starts to form. When the oxygen gets halfway, and that's halfway in energy, you reach what's called the transition state. That means trans is across, so the oxygen is going across from N to C, or they also call it the activated complex because this is the complex from which the reaction will actually happen. Now, even from this halfway point, the oxygen can still go either direction. It can finish and go all the way towards the carbon, or it can change its mind, so to speak, and go back to the nitrogen. If the oxygen goes back to the nitrogen, you won't get a reaction. The NO2 and the CO will just bounce back apart. But if the oxygen goes past the halfway point, you will produce the products, NO and CO2. The amount of energy that it takes for the molecules to get up to the transition state is called the energy of activation, or the E sub A. This is a graph of the progress of the reaction versus potential energy. When the NO2 and the CO are far apart, they're not affecting each other, but as they start to collide, they start to squeeze together just like a spring, and that means the potential energy starts to go up. If they have enough energy to reach the transition state, they'll get there, and even at that point, the oxygen can still slide back towards reactants. Then you get no reaction, but if it slides over the top, it's inevitable that it will eventually make the products. And the energy of activation is the thing that mainly controls the rate of a reaction. If you increase the energy of activation, the rate is going to slow down because the molecules have to go over a bigger hill to get to the products. If you decrease it, the rate will increase. But there's another E on that graph. If you look at the graph, you can see that I did not draw the products and reactants at the same height. I actually drew the reactants above the products. In order to go down in energy, you have to lose energy. So that in this reaction, the reactants are losing energy as they go down to products. The thing that is called thermodynamics. That delta E is primarily what determines the position of equilibrium, or the KEQ value. In order to understand this, you have to understand a very basic idea, which is kind of a combination of all three laws of thermodynamics. We're going to study all three of those laws next class. The basic idea is that all systems tend to try to reach a minimum energy, which is referred to as more stable. In other words, things don't try to increase in potential energy, they try to decrease, which the best illustration of that might be that obviously if you drop a stone, the stone is going to fall to a lower potential energy, not float. All systems are like that. So there's actually two different possibilities. The graph that I showed you in the beginning, the left side, the delta E shows that the energy decreases as you go from reactants to products. The way you decrease energy is that you have to give off energy, and then the energy of the system goes down. You remember from 131 that reactions that give off energy or heat are called exothermic. This type of a reaction is going to favor the products because they are at a lower energy than the reactants, and everything tends towards a lower potential energy. Since the products are favored, the KEQ will be large because the numerator is bigger. Whenever you have a large KEQ, that is called favorable, and you tend to favor the products. The other reaction is an example of the opposite. The products are at a higher level than the reactants. That means that the reaction is going to favor the reactants, and in order to go up in energy, the energy has to be absorbed. Reactions that absorb energy are called endothermic, and they're going to have a small k because the reactant amount is going to be larger than the product amount. Now, with that understanding, the point we're trying to do is to get an equation that will predict the rate from the math of the molecules. In order to do that, we have to discuss some of the factors that affect the reaction rate. First of all, if you powder up the reactants, they're going to react faster because they have more surface area, and it's just like increasing the concentration. Everybody knows that sawdust will burn a lot faster than a big log. That's an example. The concentration of reactants affects the rate because if you increase the concentration for either first or second order, the rate will increase. But those are not the most important factors. It turns out that the things that affect the rate more than anything are the temperature and the energy of activation. They show in organic chemistry that you can double the rate of a reaction by increasing the temperature a very small amount, approximately 10 or 20 degrees C for a lot of reactions. The reason is that the molecules are distributed according to what's called a Boltzmann distribution, and that is exponential. If you look at a sample of molecules in either the liquid or gas phase, the energies of the molecules, most of them are at a certain average temperature, but there are also ones that move very slowly and other ones that move very fast. If you increase the temperature, you know that you increase the speed of the molecules, and therefore they move towards higher energies. That's the reason why increasing the temperature increases the rate. The energy of activation line that you see on this graph is constant. You can't change the energy of activation by changing the temperature, because the energy of activation is a product of the molecules themselves. It takes a certain amount of energy for A and B to get to the top of the energy of activation hill. But you can change the rate that the molecules are moving. At a low temperature, the only molecules that have enough energy to get over the energy of activation bump are the ones that are shown in blue. And that's not very many, so the reaction is relatively slow. If you raise the temperature, all of the molecules in the orange area are now able to get over the energy of activation bump because they have a high enough energy, and that is going to speed up the reaction a lot. The other way to dramatically change the rate of a reaction is by changing the energy of activation. But that's not very easy. The energy of activation is pretty much a constant, but you can change the energy of activation for an overall process by adding what's called a catalyst. Catalysts speed up reactions, but they're the same before and after. They don't change overall. The way the catalysts work is by making the energy of activation for a reaction smaller. We're going to do an example in class next time where we study hydrogen peroxide decomposing to oxygen. You can see that without a catalyst, it has a very high energy of activation. But when you put a catalyst in, what it does is it splits the reaction into two parts. And each of those parts has a lower energy of activation, so that even though there are two reactions instead of one, the rate is much faster because the energy of activation goes down. The thing that does not change with a catalyst is the position of equilibrium. You're not going to get any more O2 and water at the end. It's just that you're going to reach equilibrium a lot faster. This is the equation that shows that you can actually calculate the rate from the math of the molecules. And for small molecules, this equation is very accurate. As the molecules get bigger, it gets less accurate, and you have to make more and more corrections to get it to work. But for small molecules, it's a pretty good approximation. This is called the Arrhenius equation, and it says that the rate equals that factor z first. The z factor is mostly the concentration. It has other contributions, but you can think of it as the concentration. That is only multiplied. But if you look at where the energy of activation and the temperature are, they're in the exponent of E, which is the base of the natural logs. So you know that exponents are going to affect the rate a lot more than things that are multiplied. That's the reason why the energy of activation and the temperature have so much more effect than the concentration. The R in the equation is just the same gas constant that's in PV equals nRT. So the thing about it is, though, if energy of activation and temperature affect the rate so much, why do we worry so much about concentration? Well, the truth is EA and T are usually constants. The energy of activation is a property of the molecules, so usually doesn't change, and the temperature is usually constant. You run the temperature at room temperature or boiling water bath. So usually the concentration is all you can change. That's why we worry about it so much. But the point of this is that the way to affect a reaction the most is to try to change the energy of activation or the temperature. And as I said, this is the equation that accomplishes what physical chemists want to do. The math of the molecules is mostly found in the energy of activation. You can estimate the energy of activation from the math of the molecules. And for small molecules, this equation gives a rate that's very close to what people find in the lab. So this is kind of what physical chemists wanted to do with kinetics. In the next class, we're going to talk about a specific application of kinetics, which is called reaction mechanisms, and then we're going to switch to the topic of thermodynamics.